Good afternoon, everyone. I am Mehboob from Tata Institute, Mumbai. And this second session, first lecture would be by Sneha Chaubey. She's from IIIT Delhi, and she would be speaking on super Apollonian dynamics.
Hi, thank you. Thank you to the organizers for giving me this opportunity to talk here. Okay, so whatever I speak today is a joint work with Elena Fuchs, Robert Hines, and Kate Stange. So this work actually unites 3 lines of research, seemingly different, but as the talk progresses, you'll see that they are interrelated. So the 3 lines of research I'm talking about is, so one stems back to Asmus Schmidt, where he introduced the complex continued fraction algorithm using partitions of the plane in Faraday circles and triangles. The other is, so I'm just talking about the lines of research in chronological order. So the first is Schmidt, second is the huge work which was done by Graham, Lagarius, Mallows, Wicks, and Yan on Apollonian circle packing and super Apollonian packing. And the third, which is actually quite recent, is the work by Romik on dynamical systems. So where he looked at dynamical system on a tree of Pythagorean triples, and that system was conjugate to the Euclidean algorithm which you get from the real continued fractions of the Gauss map. So our talk, this work is basically, you'll see that it is a reflection of all 3 of these works. So just to, for those of us who are not aware of Romik's work, so Romik basically introduced a dynamical system. So because because the presentation as well as I'll also be giving the board talk, so maybe I'll use the board as much as possible. So Romik introduced a dynamical system on the positive quadrant of the unit circle. And what this dynamical system did was to read off words starting from the root of the tree of Pythagorean triple to the Pythagorean triple. So what I want to say is, so you start with a base 3, 4, 5, and then along, so you have these 3 matrices, gamma 1, gamma 2, gamma 3, and any Pythagorean triple can be written as a word in gamma 1, gamma 2, gamma 3, leading to the base. So depending on the parity of of A, B, C, so if A square plus B square equals C square, depending on the parity of A, B, and C, you have 3 distinct roots. So you have 3, 4, 5, and you have 4, 3, 5, and you have 4, 3, 5, and 1 more. So basically, the system acts naturally to walk to the root of a tree of primitive. So by primitive, we mean that the GCD of ABC is 1, primitive integer. So the way he translates these triples to the unit circle, you can see that is just normalization. So you have A square plus B square equals C square. So you just map ABC to A over C, B over C. So you get a point on the unit circle. So, and the way to do this was through these three matrices, gamma 1, gamma 2, gamma 3. And what he did was, you get, so if you start with, so if you have an irrational point, then you get an infinite word expansion in gamma 1, gamma 2, gamma 3. And for every rational point, you have a finite word expansion. So how is this work related to Romik's? So one way to understand is that you can consider this work as a one dimension higher than Romik. So Romik deals with Pythagorean triples. So if you move to a dimension up, so if you move to 4 dimensions, okay. So, and now how is this related to Apollonian circle packing? So when I say 4 dimensions, so if you look at this equation in 4 dimensions, you have a square plus b square plus c square equals d square, which is the Lorentz equation. And so I'll be getting into that. The curvatures of the Apollonian circle packing satisfy that Lorentz equation. So therefore, you'll see that there is a link in this to Apollonian circle packing. Oh, no, so when I write this equation, they are integers. Yeah. Okay. Now one obvious, yeah, they are integers. Yeah. Did I say they are integers? They are integers. Okay, so you start with you start with looking at the Pythagorean triple, and then you translate the system to the circle. No, so you also okay. So there is. So I'm not getting into the details here, but I'll be doing that in my work. So you also define the map for irrational points, and then the irrational gives you a infinite expansion. Okay. So the difficulties in translating this to one dimension higher. First difficulty is that you don't have a unique path. So the Pythagorean triples form a tree, but when you go a dimension higher, you don't, the Cayley graph of the group does not form, the Cayley graph of the group which preserves that quadratic form does not form a tree. So that's the first obstruction we have. And so it's not a straightaway lifting of his work in one dimension higher. So before I get into the details, let me briefly describe some preliminaries and the setup. So we define Descartes' quadruples. So the Descartes quadruple is a collection of 4 mutually tangent circles in the plane. And corresponding to the Descartes quadruple, you have a dual quadruple. Which is just the collection of 4 mutually tangent circles which pass orthogonally So here you have a picture of the Descartes quadruple and the dual. So you have the blue circle is Descartes quadruple, 4 mutually tangent, so that the interiors do not overlap. And we orient them in a way that the interiors do not overlap. And then you have the dual quadruple, which is given by the red circles, which are the ones which pass through the tangent points of the previous 4. Now, the curvatures of the 4 circles of a Descartes quadruple satisfy a quadratic form. So the curvatures, which by curvature I just mean the inverse of the radii, oriented inverse of the radii. So circles of a Descartes quadruple satisfy this quadratic form. And in other words, they are the zeros of this if A, B, C, D is a Descartes quadruple, then D of A, B, C, D is 0. Okay. Yeah, so A, B, C, D stand for the curvatures of the 4 circles of a Descartes quadruple. So time and again my nomenclature will interchange. So by Descartes quadruple, I mean the curvatures as well as it's the circles which are mutually tangent to each other. So does this make sense? So you have A, B, C, D, which is the so this is the quadratic form, and if you have A, B, C, D acting on this times A, B, C, D transpose, you get 0. So you get this relation.
This is also quadratic form.
Yeah. It's the same quadratic form. Yeah.
But now it's D.
Yeah. Now okay. So maybe I'll just write it. Sorry for the confusion. Okay. So exactly. Yeah. And in fact, not only the blue circles, because so you take so if you look at the dual quadruple, that itself is a Descartes quadruple, right? Because they are also mutually tangent to each other. Okay, so in order to define the dynamical system, we introduce special coordinates for the circles, which we call as. So, well, we don't introduce this. This was done in Graham's work on Apollonian packing. So these are called the ACC coordinates, augmented curvature center coordinates. So, for this, you can look at these circles in the extended complex plane, and which is identified as P1C. And then if you look at, so if you have any circle with the condition then, so to this circle, the ACC coordinate for this circle is given by so B1 and B2 are the real and imaginary parts of P. So this is the co-curvature, this is the curvature, and this condition we just have to make sure that the radius of the circle is given by square root B square minus AC over A. So we have this condition just to make sure that the curvature is just A. Okay? So because the radius is 1 over A, if you have this condition. So to every circle, you associate this quadruple, which consists of the co-curvature, curvature, and the and B1 plus I, B2, which is nothing but center times curvature. So, for example, this will represent the real line. Okay. So the real line has this as the ACC coordinate. Now, in terms of the augmented curvature center coordinates, that condition on the quadratic form just translates to the fact that, so the 4 circles, so in terms of ACC coordinates, 4 circles CI in ACC coordinates are in Descartes configuration if you have C transpose D QC equals some matrix. Now we want to move between adjacent Descartes quadruples. So we want to extend this packing. So the way to do this is, so either you swap or you invert. So so by swap I mean, so you'll have so what you can do is you can have these 4 swaps. So by swap I mean you fix 3 of the circles and then you swap the 4th one in the dual of the other 3. So for example, you have these 4 circles, 1, 2, 3, 4, and suppose you want to swap this circle, so you fix these 3 circles, 1, 3, and 2, and then you just take the inversion in the dual of this circle. Okay, so is this clear? So 4 has this as the, so the new circle formed is 4 prime corresponding to 4, and similarly for 3 you have 3 prime, and for 2 you have 2 prime, and for 1 you have 1 prime. So these are the 4 swaps which you can do, or you can invert these circles. So by inversion, what we mean is, now you fix one circle and then you look at its inversion in the dual of the other 3 circles. So for example, if you, so suppose you want to, so you have these 3 circles, and suppose you want to invert this outer circle, then the you keep the outer circle fixed and then you invert each of these. So you have this, this, and this. So basically you have this outer circle and the 3 of these black circles. So that's how you move between adjacent Descartes quadruple. So so this is the geometric interpretation of moving from one Descartes quadruple to other, but algebraically this means that you have this group which is called the super Apollonian group, which is nothing but generated by, so each of these geometric action can be viewed as a matrix. So you have this group AS which is generated by these matrices Si, and the inversion is just the transpose of these SIs, and with the condition that these are involutions, and you have this commutative relation. This is the presentation of this super Apollonian group. So So algebraically, this means that you have the super Apollonian group which acts on the Descartes quadruples, and it gives you these partitions of the plane into triangles and circles, into triangular regions and circular regions. Now, there are two natural ways to write. So any element in the Apollonian group will be written as the generators will be written in terms of SIs and SI transpose. Now, there's a natural way to uniquely write elements of AS, which is given by the swap normal form. So if you just go back to Romik's case, the group there, if you look at the Cayley graph of that group, it's a tree, and hence there's only one unique way to write elements. But here you don't have a tree, so you take the spanning tree of the Cayley graph of AS. So, and we choose two of these. We choose these two special spanning trees given by swap normal form, and invert normal form. So the swap normal form is defined by, if you have a word in SI and SI transpose, let's say Mn minus 1 M1, then the swap normal form is that if Mi, so first of all, Mi should not be equal to Mi plus 1, and Mi, if Mi is equal to Sj, and Mi plus 1 is equal to Sk perp, then J is equal to K. And for the invert normal form, you have the same condition in A, and for B you have if Mi is equal to Sj perp, and if Mi plus 1 is equal to Sk, then J is equal to K. So basically you're pushing the swaps to the far left. So if Mi equals Sj perp and Mi plus 1 equals Sk, J equals K. Now, the orbits of the super Apollonian group on a quadruple, Descartes quadruple, is called a super Apollonian packing. So for those of us who knew, so for the Apollonian packist here, the Apollonian packing is the orbit of the group S1, S2, S3, S4 acting on the Descartes quadruple. And for the super Apollonian, you also include the inversions. So Apollonian is just the swaps, and super Apollonian is swaps as well as inversions. So basically, it's just a picture of if you iterate your swaps and inversions, so you have the base, so suppose you start with that base quadruple, and you iterate with swaps and inversions, you get finer partitions of the plane in, so that's the first, so this is the first generation, that's that picture on the far left, far right, sorry, this one is the second generation, and then again if you apply swaps and inversions, you get this, and so on and so forth. So you get this dense packing. Now what we do is, so this group can now be geometrically realized as an embedding on the complex, as an embedding, so AS can be realized by embedding it into PSL2C. So Mobius, so for each SI, we want to view it as a Mobius transformation, but not exactly a Mobius transformation. You take the direct product with the conjugate as well. So this basically stands for the conjugate action. So you can view this group by embedding it into this, and now since I only have 5 minutes left, I'll just maybe I'll not write much, and I'll just say what we want to do here is. So now you started with writing quadruples as words in SI transpose, and each of these can be realized as a Mobius transformation. Now each of the these Mobius so for each S1, so for each S1, S2, S3, S4, and their transposes, you have corresponding Mobius transformations, and then you associate to each region a Mobius transformation. So for example, for the so this is the second generation, right? So for the first generation, you will have S1. So each of these 8 regions will be coordinated by a Mobius transformation corresponding to SIs and SI transpose. And then in the second generation, you will have words of length 2. So each of these triangular and circular regions will be coordinated with words of length 2 in SIs and SI transpose, which are the Mobius transformation corresponding to capital SI and SI transposes. So basically what we are trying to do here is that we are trying to coordinatize the plane by words in Mobius transformation, and then you try to write a dynamical system which gives you the coordinate of a point in terms of those Mobius transformation. Okay, so maybe I'll quickly jump to writing the dynamical system which we get here. So you have these maps on these regions. So you fix for a fixed Descartes quadruple RB RA. So RA is the dual of RB. You have these so by RB I mean this. So RB represents a Descartes quadruple, so it's a set of 4 circles, and we take this as the base quadruple. So you have these 8 regions. Let's just call them as A1, A2, A3, A4, and so you have these 8 regions, and these are the intersection points of the circles. So on each of these, you define the map TBZ. So this is nothing but, so you swap if your Z is in this region, and you invert if Z is in BI. And similarly, corresponding to the dual of RB, which is this, you can define a map TA. And now, under this dynamical system, we show that so if you have a Gaussian rational, then it reaches one of the fixed points. So the fixed points of these maps are the tangency points, and because the tangency points were simple enough, we chose these as a base quadruple. So it reaches one of the fixed points in finite time. And the point at which it reaches to, it's determined by the parity of the numerator and the denominator. So, and finally, finally, what we do is, so to each of these words, as you saw that we associate an open circular or a closed triangular region. So Z goes to a word every Z. Okay, so what's happening here is you have a complex number, you associate it to a word, and now to a word you associate a closed triangular region. So, for example, if you have a complex number belonging to this circular region, then you associate this word to that number. So, doing so, what happens that you translate this dynamical system to writing complex numbers as words in these circular regions, and finally you get a rational approximation. So this is a type of continued fraction algorithm. You get an approximation of the complex number you started with. So for example, just to quickly end, so if you have a point, so let's see, so you have this rational number, and now this rational number is inside this circle, okay? So you start with S3 perp, because this represented, so if you go back to that picture, this region represented S3 perp, and then on the for the next generation, when you apply the iterate of this map, you get closer to that point, you get S3 perp, S1 perp. So you have, in the next generation, these are the circles in the next generation, and then in the third generation you have these new circles, and so you get an approximation of the complex number. And this approximation is good enough because it coincides with the Schmidt's continued fraction algorithm, and the constant which we get is the best possible. So the paper is already there on arXiv, so you can go and have a look at the approximation. Thank you.